So in last session we discussed about the normal and tangential coordinates, how we can describe a curvilinear motion using a set of nt coordinates. Normal axis is perpendicular to tangential axis is at different time instants tangent to the path of the particle, right? So after the introduction we discussed how we can determine the velocity and acceleration in this coordinate system. So for velocity, if you remember, we came up with this expression at the bottom, that velocity vector is equal to rho times beta dot times E sub t unit vector. E sub t is the unit vector in the tangent direction, so it is a unit vector here in the tangent direction, and the magnitude of velocity will be equal to rho times beta dot, where rho is the radius of curvature and beta is the angle, right? Angle between initial and final point which the curve path is making at the center of curvature, right? Dot represents the first derivative of its quantity, so beta dot means d beta by dt, right? So here we saw that the velocity vector do not have a normal component, it is all in the tangential direction. So there is no two components of velocity, one in normal direction, one in tangential direction. Velocity only have the tangential direction, right? So velocity vector is represented this way, and the corresponding scalar relationship will be v is equal to rho beta dot, right? Similarly, we have seen how we can describe the acceleration vector in this new nt coordinate system. Here you have seen that acceleration have both components. One is in the normal direction, one is in the tangent direction. But in the initial formulation, we saw that there is a quantity which is the first derivative of the unit vector appearing in the acceleration expression. So we evaluated that quantity, this first derivative of the unit vector E sub t with respect to time. We determined that quantity and that came out to be this thing at the bottom, that the first derivative of unit vector E sub t was equal to beta dot time E sub n. When we introduce this expression back in the original acceleration equation, we exactly get both components of acceleration, because one quantity, one term was having a direction E sub n, other was having E sub t. So it means that the magnitude of this second term, we can call it the magnitude of the tangential component of acceleration, and the magnitude of this first term, we can call it the magnitude of the normal component of acceleration, right? So finally we can write acceleration in terms of some quantity times E sub n plus another quantity times E sub t, right? And those two quantities are the magnitudes of A sub n and A sub t, where A sub n and A sub t are the normal and tangential components of acceleration. And finally we can write also the magnitude of total acceleration will be simply A sub n square plus A sub t square root, right? So let's now, before moving forward, quickly summarize what we have discussed up till now. We know that velocity vector is equal to rho times beta dot times E sub t unit vector. Similarly, acceleration vector is equal to v square over rho times E sub n plus v dot times E sub t unit vector, right? This gives us several scalar relationships also. For example, v is equal to rho beta dot, right? Similarly, this quantity v square over rho is the n component of acceleration, magnitude of n component of acceleration. So it is v square over rho, and this can also be written as v beta dot. So this is v beta dot also, and there is another form also in which we can write this expression, and that is here rho beta dot square, right, at the bottom right. rho beta dot square. Rho beta dot square. So you can see that if you use this expression, you can convert from this to this or this to this, right? So all three are actually the different forms of the n component of acceleration. Similarly, a sub t, the magnitude of the t component of acceleration is v dot, right? And we can finally write the acceleration vector as a sub n times e sub n unit vector plus a sub t times e sub t unit vector. The magnitude of a vector will simply become a sub n square plus a sub t square root, right? So these are all the relationships which we have studied. Once we are able to write the velocity and acceleration in terms of n and t coordinates, right? We can also draw some conclusions from these relationships. First of all, it is obvious that, for example, velocity do not have any normal component. It only is in the tangent direction. So v is just one term, but acceleration have two terms, one component in n, one in t. One other conclusion which we can draw from these relationships is that at the point of inflection, we have seen that there is no curvature, or in other words, the radius of curvature approaches to infinity. And if we put rho as infinity here, we will get a sub n as 0, right? So it means that at the point of inflection, a actually will approach to a sub t, or acceleration will be all in the tangent direction. There will be no normal component of acceleration, right? So for example, if the curved path looks like this, so exactly at this point you have the point of inflection, right? And at this point there is only tangent direction of acceleration, that will be something like this. So no normal component, so there will be this n axis and this will be like t axis, right? So there is no acceleration component in the n direction. So you can also think of in this way that for that particular instant of time, the curvilinear motion becomes a rectilinear motion only in the direction of t, right? So there is no second component of acceleration there, right? But at any other time instant, at any other point along the path, you may have both components of acceleration, n and t components. Another conclusion we can draw from the same expression is that if a particular particle is moving in circle with a constant speed, so for example, circular path plus constant speed, right? Constant speed will mean v dot is equal to 0, right? So if a particle is moving in circle with constant speed, means v dot equal to 0, right? Or any curved path with v dot equal to 0, in that case the a sub t will become 0, right? And the acceleration will have only normal component, so which means a sub t is equal to 0, and a will only approach to a n, or acceleration will only have a normal component, right? No tangent component if a particle is moving with a constant speed, which means v dot is 0, right? After this introduction, let's quickly look at the geometric interpretation of this same equation. For example, this equation at top, or for example, any of the component equations at the bottom, right? So we can come up with the same relationship geometrically also by visualizing different vectors, acceleration vector, velocity vector. So in order to have a geometric interpretation of this same equation, let's go back to the same figure which we discussed last time, and that figure said that if a particle is moving in a curved path, right? So this is the path, and at one time instant it was at point A, and at next time instant it was A prime. So this whole motion is occurring in time equal to dt, right? So during time dt, that motion occurred from A to A prime, and if I represent the velocity vector of that particle at point A as v, and the velocity vector at point A prime as v prime, with this notation, what we can do, we can start both of these velocity vectors from the same point and try to calculate what is the difference in these vectors. So the change in velocity vector we can determine and then see how the acceleration can be written in terms of that change in velocity vector. When we do that exercise geometrically, we will come up with the same equation which we have seen in this last slide, this same equation at the top, right? So what I am doing now is I am starting the v vector and v prime vector, this vector and this v prime vector from the same common point, right? And since the normal axis at both points A and A prime, they were making an angle d beta with each other, so their perpendiculars, which means the tangential axis, will also be making the same angle d beta with each other, right? Because with this normal axis you have a perpendicular this one, and with this normal axis you have a perpendicular this one, right? So whatever angle those normals are making, their perpendiculars should also make the same angle, so which means that this angle is also equal to d beta, right? So I get a triangle which is actually having v vector and v prime vector as its sides, and a vector quantity which is starting from the tip of v and ending at the tip of v prime is actually the change in velocity vector, right? So dv vector is the change in velocity vector. It is equal to v prime vector minus v vector. It is the velocity change, vector change in velocity, and it also defines the direction of acceleration. We know that the direction of acceleration is always in the direction of velocity change, right? So this dv is the change in velocity vector starting from the tip of v vector ending at the tip of v prime vector. Now we know that velocity at a given time instant is in the tangent direction. So this is our t direction and this is our perpendicular to that is our n direction, right? This is positive n because it is towards center of curvature if you consider that last figure in mind. So any direction in this direction will be plus normal direction, right? Now what we can do is that we can resolve this dv vector into its two components, one along t, one along n, right? So what I am doing, I repeat that I am resolving this change in velocity vector into two components. One will be called dv sub t. dv sub t means the t component of the change in velocity vector, right? T component of dv. Similarly, I have the dvn, which is the n component of dv, right? So I resolve the change in velocity along t axis and along n axis. Obviously the acceleration's t component will be in the direction of dv sub t, right? Acceleration is the change in velocity divided by time, right? Change in time. So d sub v t will have the same direction as a sub t, acceleration's t component, and similarly dv sub n will be the n component of dv, and the n component of acceleration will also be in the same direction, right? The acceleration total vector will be in the same direction as the change in velocity vector, so you will have the acceleration vector in the same direction as dv, right? So after this notation is clear, let's now write what is dvt and what is dvn, because if we can calculate dv sub t vector and divide it by dt, what this quantity will become? A sub t, because this will become the tangent component of acceleration, right? So this quantity is the change in the t component of the velocity change vector which will become actually the acceleration's t component. Similarly, if we can determine dv sub n divided by dt, this quantity will actually become a sub n vector, right? So let's try to determine what is the magnitude of dv sub t, what is the direction of dv sub t, and similarly what is the magnitude of dv sub n and direction of v sub n, right? So let's start with the dv sub n first, right? This vector which I am encircling now, it is the component of dv along n axis, right? Now n component of dv, its length actually should be equal to, again I can apply that formula, L is equal to r theta, that if the length of point A and B is equal to small l, this distance from some origin to A is r, and it is making an angle theta between A and B at the center, then L will be equal to r times theta. So the magnitude of this dvn actually should be, when you simply rotate this v vector here by an angle d beta, right? So the length of this dvn should be equal to the magnitude of this v vector times the angle which it is making, this angle, right? So the magnitude of the dvn is equal to length of the arc generated by swinging v vector through an angle d beta, right? So applying that formula, L is equal to r theta, we can write the magnitude of dvn by denoting it with these two lines. It will simply become the magnitude of the v vector times the angle. So this is like r times theta, right? And this is equal to, for example, that length, right? So r is the magnitude of the v vector, and it rotated along an angle which is equal to d beta. This will simply become v d beta, right? Where v is a scalar quantity representing the length of the v vector, right? And if we simply divide the magnitude of this dvn by dt, right, this becomes the n component of acceleration, or magnitude of the n component of acceleration. So we can divide this v d beta by dt, and in our notation it will become v times b dot, right? So here we have seen that the n component of acceleration, which should be actually the magnitude of the n component of change in velocity divided by change in time, that becomes v times beta dot, same as what we saw analytically in the last slide, right? So a sub n, actually this vector will have a magnitude a sub n, magnitude will be equal to v times beta dot, and we have seen it geometrically also now, right? If I go back, you have seen that already this expression an is equal to v times beta dot, you have seen that before also, but now geometrically also you have determined this a sub n, and that is equal to v times beta dot. Now you can also convert it into v square over rho and the third term also, right? Similarly, let's talk about the t component of change in velocity vector, which is dv sub t, right? First of all, its magnitude. Its magnitude should be simply equal to the change in the length of this v vector, because v sub t, dv sub t is in the tangent direction, right? So in tangent direction, the change is only occurring in the magnitude, right? So therefore, the magnitude of this v sub t should be simply the change in the length of v vector. There is no direction change here. In the first case, v vector was changing direction also, but in the second case, dvt and v vector have the same direction, that is t direction, right? So change in velocity in the same direction is simply the change in the length of that vector, which is velocity vector. So the magnitude of dvt vector will be simply equal to dv, which is change in the length of v vector. If we divide that with dt, it becomes the t component of acceleration, change in velocity divided by change in time. So the t component of acceleration will be simply dv by dt, and we can represent it as v dot, or the second derivative of displacement. Again we have reached to the same equation, which is a sub t equal to the first derivative of speed, which is v dot, right? So we have seen that equation earlier also, so we reach to the same equation again, a sub t equal to v dot, right? So geometrically we reach to the same two components of acceleration by resolving the change in velocity vector along n and t directions respectively. So this actually answers the questions like why this quantity need to be the n component of acceleration, or why this quantity at the bottom need to be the t component of acceleration, right? So you have seen that in the geometric form also. So now we can have another description of a sub n and a sub t also. If you look closely, what is happening here, you are having the change in velocity vector dv, and then you are resolving it into two components. One component is giving you the a sub n, other component is giving you a sub t, right? Now this dvn vector is simply the change in direction of v with respect to time, right? So dvn is simply the change in the v vector in the direction of n component, right, in the n direction, and this dv sub t is simply the change in length of v vector along the same t axis, which is the original direction of v vector, right? So if we say that the velocity changed during the time dt, so for example velocity changed, right, during time dt, and that change occurred both in magnitude and direction. So that change is actually magnitude also changed, right, and direction also changed, right? So if you look closely, a sub n is actually representing the component of acceleration which is taking care of the change in direction of velocity, a sub n. And a sub t is the component of acceleration which is taking care of the change in the length of v vector or speed of that particle. So a sub t is actually related to this effect, and a sub n is related to this change in direction of v effect, right? So therefore you have seen that a sub n is simply equal to v square over rho, right? But the a sub t is equal to v dot, right? How fast the velocity is changing, the speed is changing actually will actually tell you what a sub t is, right? And what is the radius of curvature, it will affect the a sub n, right? So in short, we can also have another interpretation of a sub n and a sub t. A sub n is the component of acceleration responsible for direction change of velocity. A sub t is the component of acceleration responsible for magnitude change of velocity, right? Now let's have a couple of examples in this topic, but before doing that, let's apply the same relationships which we have discussed up till now to the circular motion case. Circular motion is a special case of curvilinear motion, right? So it is a case of curvilinear motion, and that can be more naturally or in a straightforward way described using n-t coordinate system. So in circular motion we know that first thing is that rho becomes constant, right? Rho is the radius of curvature, and that simply becomes the radius of that circle which the path is making, right? So if the particle is moving in a circular motion, it will always maintain a distance r from the center of that circle. So which means rho will equal to the r, where r represents the radius of circle, right? The second thing is that we can also now replace this beta with another symbol theta, where theta represents the angle from any reference line to the normal axis which the particle's path is making, right? So if particle is at point P, its acceleration will have two components, a sub t and a sub n. A sub n will always be towards the center of curvature or the center of circle now, and a sub t will be tangent to the path. Velocity vector will also be tangent to path, right? So in this particular case, we can simply replace beta with theta, and theta will be the angle which from any reference line, for example, if we take this line as the reference line, so starting value of theta will be from this point to the normal axis of the particle's path, right? So we can replace beta with theta, and then our three equations will simply become rho will be replaced by r and beta will be replaced by theta. So V becomes r times theta dot, a sub n becomes V square over r, or r times theta dot square, or V times theta dot, right? So all three equations will simply take new form or new notation. Similarly, a sub t will become V dot, and that will be same as V dot here, but if we simply put V is equal to r theta, right? So we can take r out, and this will become the, so for example here we can put V is equal to r theta dot, so a sub t becomes d by dt of V, and that is r theta dot, right? R is a constant quantity in circular motion, so r can be taken out of the equation, and the theta dot will become theta double dot, right? So a sub t is equal to r times theta double dot. So in circular motion case, we can directly apply these three equations if we decide to describe that circular motion in terms of n and t coordinates, right? So it is very important that for any given problem you identify exactly what coordinate system will remain suitable to describe that motion, right? So if you have a problem of projectile motion, I would suggest to always use the xy coordinate system. If you have a circular motion case, you can either use nt coordinate system or polar coordinate system. Both will actually result in same equations we will see in next weeks when we will be discussing polar coordinate system. So you can use either nt coordinate or polar coordinate to describe the circular motion. If for example there is a general curved path and you know that something related to the radius of curvature and center of curvature is included in that problem, which means nt coordinate system should be used to describe that motion, right? So please think of resolving the acceleration in that problem into n and t components, right? One more thing related to the application of this coordinate system to circular case, that this quantity theta dot, the rate of change of theta with respect to time, is called angular velocity, and it has the units of radian per second because it is d theta by dt, right? And theta is in radians, right? So the change of theta with respect to time, actually this whole quantity should have the units of radian per second. You can also convert radian to degrees, so it can also be degrees per second, right? So in US units it will be same units but different symbols. So seconds will have SEC symbol instead of S. In acceleration, both terms you can see, first of all an is containing a quantity same theta dot, but a sub t is containing a quantity called theta double dot, and this quantity is called angular acceleration, and its units will actually become radian per second square or degree per second square in SI system. In the US system also same units but different symbol, right? So now you are also familiar with what is angular velocity and angular acceleration. The rate of change of theta with respect to time is angular velocity. So how fast theta is changing, right? And the rate of change of theta with respect to time, like the second derivative of theta, will become angular acceleration, right? So one last thing before we go to the solved examples is that you can convert degree per second to radian per second or vice versa. The conversion from degree per second to radian per second is, if I talk about for example US systems, and same is also in the SI system, you have to multiply by pi by 180, right? So for example, if I ask you to determine 90 degrees into radian per second, you have to multiply 90 by pi by 180, and this will become pi by 2, right? So please note that whenever you use beta or theta in curvilinear motion described by the anti-coordinate system, please do not confuse between degrees and radians. If you are taking length in meters or feet, if you are taking other quantities in standard units, right, the angle is always in radians unless you explicitly convert it into degrees, right? So otherwise the angle will remain in radians. Similarly, for converting degree per second square to radian per second square, same conversion, because the quantity which is actually changing is the numerator, degree to radian, right? Second or second square in the denominator doesn't matter. So you can simply apply this conversion factor to convert between the two, right?